Welcome to lecture number 3 for ECE 321 Analog Electronics, Push-Pull Amplifiers. Now there's a couple different types of amplifiers. There's Class A, Class B. Well, actually kind of backing up a second. One way, if I want to drive an 8-ohm speaker, I've got a problem. The op-amps that we're using in lab can't drive 8 ohms. The op-amps that we're using only have a 50 milliamp capability. So if I have an 8-ohm speaker and I want to drive it, what I could do is take one of the op-amps that we have, capable of 50 milliamps, add a resistor in series to the 8-ohm speaker, limit the current to 50 milliamps. So this is going to be at most 5 volts. 5 volts at 50 milliamps is 100 ohms. So this has to be at least 92 ohms, probably like a 100 ohm resistor. So add a 100 ohm resistor in series, and these op amps can drive the speaker. That's going to make it kind of quiet. So if you want to annoy your friends and neighbors, I need more power. One way is to buy an op amp capable of driving 8 ohms. Those do exist. The OPA 2544 can do it, but that's $18. The advanced smoker devices, AMD 38AT, something like that, can also do it. That can do 20 amps, but that's $400. Can I drive a speaker using $1? Because I'm cheap. Answer is yes. That's a transistor amplifier, Class A or Class AB. Now the load lines for a transistor circuit, again, if I have a transistor right here, it's got a load line. This is what we've been doing before. At this point, the transistor's off. At this point, I'm saturated. In digital electronics, those are the 2 points one operate at. It's either going to be off or on. And if you're a Star Wars fan, like the Sith Lords, it's black and white, for me, against me, on or off, nothing in between. And I need that because I'm going to be saturating a transistor. Well, in analog electronics, I don't want to do that. I want to operate over here. The reason being is if I have a sine wave coming in for current, I want to go up and down the load line and get a sine wave out. Over here on the off side, I'm going to saturate. Over here, I'm going to clip. I need to be in the active region. That's called a Class A amplifier. The problem with the Class A amplifier is if there's no signal coming in, I am still drawing current, meaning I'm still dissipating power. So this is really inefficient. A second type of amplifier is called a Class B amplifier. That's where I operate at this point. The nice thing about that is if the input is 0, the output is 0, I have no current draw, so it's a little bit more efficient when it's sitting there idly. The problem, though, is you've got a transistor like this. Just for fun, let's call this ground. If this goes below 0, I'm trying to pull current through that diode. That can't happen. Transistor turns off. So what happens is to have a sine wave coming in, the output isn't a sine wave, it's clipped. I can go left, I can go up the load line, but I can't go down because going down produces energy and a transistor cannot produce energy. I clip at 0. So what comes out is a clipped sine wave. What you can do is do a push-pull amplifier. Got to get ahead of ourselves a little bit. What a push-pull amplifier does is, well, up here, this is an NPN transistor. That's on the push side. What we're going to do is have an NPN over here, driving my 8-ohm speaker. So that's your NPN. And notice this is a little bit different than what we did back in digital electronics. On digital electronics, the load went on the collector side. In analog electronics, it goes on the emitter side. Here's the emitter, collector, base. The reason being is if this is your input, and that's a sine wave, let's say less 5 volts peak, this is 0.7 volt drop, this will be 4.7. As the base goes up and down, the emitter goes up and down with it, giving you what you want. A sine wave in gives you a sine wave out. But I can't go negative, so this is the push part. I can push current through the load. There's a second part called pull. That's a PNP. We haven't dealt too much with PNP transistors. Here we will. For the push part, I need a power supply, like plus 10 volts. On the negative side, I need another power supply, say minus 10 volts. This is the pull part. When the current goes negative, this diode turns on, and the PNP follows it. This is a 0.7 volt drop, so as they go negative, the PNP turns on. That's your push-pull. This is a class AB amplifier. When the input is 0, the output is 0. I'm right here. But when I push, the NPN turns on. When I pull, the PNP turns on. So that's what we're going to be doing. And you kind of see that. If you look at a stereo, this is like a hi-fi stereo. It's got these two sections right here. This is one pair of push-pull amplifiers, the NPN, PNP for the left channel. Here's another pair for the right channel. And notice, these are connected to the big heatsink. We didn't do that in digital electronics. In analog electronics, you do. The reason being is power. If I say have a 10 volt source, I want to have 5 volts across my 8 ohm speaker. Then I also have 5 volts across my transistor. So the transistor dissipates just as much power as the speaker. It's going to get hot. Speaker turns the energy into heat and sound. Transistor just turns it into heat, so I need a big heat sink. That's characteristic of analog electronics. They're going to get hot. You need a heat sink. That also lets you tell the difference between analog and digital transistors. Analog transistors have a big heat sink, or designed for heat sink. Digital transistors aren't necessarily designed for that. You can use the analog transistors as switches. They're not designed for it, but they work perfectly well for that. The digital transistors, the little bitty ones that look like this, they're not designed to dissipate heat. You really don't want to use those for analog. So, back at the ranch. Again, I want to drive an 8 ohm speaker, and I want to have the relationship y equals x. And I want to spend less than $18 on the op amp. That'll be today's solution, a push-pull amplifier. So, starting out with the push side. Suppose I want to drive an 8 ohm speaker and I have a 5 volt input. What I could do is have a transistor where the speaker is attached to the emitter. Again, different than digital electronics. Here it's connected to the emitter, not the collector. If I do that, this is a 0.7 volt drop, so this is going to be 4.3 volts. Well, it actually kind of depends upon the transistor. If I go to DigiKey and look at the 6144, here's one of the transistors that we're using in lab. If you look at the voltage, let's see, is it in here? Oh, data sheets. Time passes. So here's the data sheet. What I'm looking for is the voltage base to emitter. Kind of notice these have a weird pinout. You'd think that the base would be in the middle. It's not. It's actually on the left. It goes base, collector, emitter. So you got to make sure you got to get them right when you power them up. And the voltage base to emitter is right here. That's at most 1.2 volts, typically 0.7. This is just a transistor. The voltage drop across the silicon transistor is 0.7. The other transistor we use are the TIPs. TIP112 is NPN. TIP117, I think, is the PNP. This one is a little bit different. It's a Darlington pair. What that means check out the data sheets. Let's see, how do I make this bigger? That worked. This is what's inside. It actually has two transistors. The reason they do that is it's hard to have a high gain and high current capability in a single transistor, so they have two. This one has a gain of like 10 and a high current capability. This has a gain of 100 and a lower current capability. Put them together, I have a gain of 1,000 and capable of 3 amps. So that's the nice thing about the TIP112, capable of 3 amps and a gain of 1,000. The disadvantage is I have two transistors in the package, so the voltage drop base to emitter is 1.4 volts. In addition, there's the flyback diode right here. If you put it in the circuit backwards, this will short out the transistor. So you got to get the collector on the high side, emitter on the low side. So anyway, back over here. Depends upon the transistor you're using. If you're using a 6144, this is 0.7 volts. In this case, I guess I'm using a TIP transistor, so the voltage drop is 1.4, making this 3.6 volts. The emitter will follow the base up and down, just 1.4 volts below. So that's what you're seeing right here. As the base voltage goes up, the emitter follows it, down by 1.4 volts, until the transistor turns off. When it turns off, there's nothing across the 8 ohm load. That's the push side. There's also the pull side. On the pull side, you use a PNP transistor. This is when the voltage goes negative. So like if X is minus 5 volts, here I've got a 1.4 volt drop. Again, using the TIP transistors, they're Darlington pair, I'll have a 1.4 volt drop. That'll make this minus 3.6 volts. And you get this kind of characteristic. Up here, this is push. That's the NPN. Over here is pull. That's the PNP. And the transistors are alternating. I go push, pull, pull. That's driving the speaker up, down, like you want. Notice, however, there's a thing, that little elbow right here, that's called the, I forget the name of it, crossover distortion, that's the name. When I'm less than 1.4 volts, the NPN doesn't turn on. Less than minus 1.4 volts, or closer to ground, but to minus 1.4 volts, the PNP doesn't turn on. In this region, the output is 0, giving you this little elbow in the output. That's your crossover distortion. Very common with a push-pull amplifier. To get rid of the crossover distortion, what I do is I add an op amp. With an op amp, V plus equals V minus. So this is the same. Take that V minus. Actually, what I would do when I build this, first thing I do is build a voltage follower like this. V plus equals V minus. This is X. That gives you exactly the same circuit we had before. I'll have Y equals X plus or minus 1.4 volts. I'll get that crossover distortion. Next, when I build this, the first thing I would do is just use the two transistors. Make sure I'm getting pushing and pulling. Connect the speaker here. I should see the speaker go up. NPN is working. See the speaker go down. PNP is working. Transistors are working. So far, so good. Add an op amp as a voltage follower. Again, I should see the same thing. When X is positive, speaker goes up. X is negative, speaker goes down. Crossover distortion. That convinces me that the op amp is working. I kind of do that because if I can't get a voltage follower to work, nothing else is going to work. And sometimes op amps don't work. The ones we have in the lab sometimes get abused. If you get that to work, then connect V minus to Y. So now if this is 5 volts, this is 5 volts, this is 5 volts. Plus 1.4, that'll be 6.4 volts. That's on the plus side, push. If I go on the minus side, pull, when this is minus 5 volts, this is minus 5 volts. And this will be minus 5, minus 1.4, minus 6.4 volts. So if I look at the input versus output, here's what I get. X equals Y. The two are the same. What's happening is I have push NPN, pull PNP. That's my push-pull amplifier. If I that's kind of what I just did. Make it 8 volts in, I have 8 volts out, minus 8 volts in, minus 8 volts out. Output equals input. If you check that in Circuit Lab, let's see if that works in Circuit Lab. So here's my push-pull amplifier. In this case, I used a Darlington pair. Depends upon which one you're using. If you have a TIP transistor, that's a Darlington pair. Go into Circuit Lab and scroll down. Scrolling, 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 scrolling. There's the Darlington pair. You can see the two transistors in one. If you're using a, oops, I just do. If I use the 6144 transistor, that's just a single transistor. I would use this model. But assuming I'm doing the Darlington pair, I'm going to do push-pull. Here's a 2-volt sine wave input. Initially, I'm just going to do voltage follower. That would be the first thing that I would check. Let this puppy run for 2 cycles, for 2 milliseconds. Make the step size 1,000 times smaller, 2 microseconds. Let her run. Here you'll see the crossover distortion. It's a little bit slow because when I switch from push to pull, pull to push, that's a little bit difficult on the simulation. It's a big switch from the NPN turning on, then suddenly the PNP turns on. Okay, and that's what I want. So here's the input, 2 volts. There's the output. It's about 1.4 volts below. That's the voltage drop across the Darlington pair. And here's your crossover distortion. So far so good. If I now take this wire, and instead of connecting it as the voltage follower, I go over here. Now for an op amp, V plus equals V minus, V4 equals V1. So when I run that, again, a little bit slow because I'm kind of pushing the simulation without switching between NPN, PNP. Here's what I see. So here, V1, let's turn this on and off. Here's the input. Here's the output. You can notice that the input equals the output. That's what I want. If you're curious, this is the voltage at the base. When I'm pushing, I'm 1.4 volts above the output. That's to turn on the NPN. When I'm pulling, I'm 1.4 volts below the input. That's pulling, pushing, pulling. And this part right here is where I suddenly switch from push to pull. That's what makes it hard on the simulation. So that's working. This is with a 100 ohm load. If I change that to 8 ohms, this should also work. So that's the push-pull amplifier with a gain of 1. What I would do in lab is kind of do it in stages. Just have an amplifier with a gain of 1. Its sole purpose is to drive the speaker. And what that does is I can have 8-volt sine wave right here, capable of 0 milliamps, or actually capable of like 1 microamp, driving the op amp. I can then drive 8 ohms at 8 volts. I can drive 1 volt, 1 amp at the speaker. If I want to have a higher gain, do that with what we did yesterday with an op amp circuit. But you can actually build a push-pull amplifier with a gain. That'd be this circuit right here. So here, this is actually a voltage amplifier. Where you want to use voltage is for speakers. Voltage drives the speaker. Can also be current. For a motor, voltage is speed. If you have a DC motor and want to control the speed of a motor, this will do it. Kind of same idea is, suppose these are both 1K resistors. Then X is 1/2 Y, Y is 2 times X. Or pick some other ratio, Y will be 1 plus R1 over R2 times X. If X is 5 volts, V minus is 5 volts, this is 5 volts, and I did that wrong. Okay, make this 2 volts, okay, or whatever. This is 10 volts. Make sure your power supply is capable of driving 10 volts, so maybe use the 15 volt power supply and minus 15. and I have y is 2 times x. If you want to simulate that in Circuit Lab, what I would do is go back to this guy, go back to build, and let's slide him over. And just to illustrate that I can drive 8 ohms, we'll make that an 8 ohm speaker. Let's have a gain of 2. So here will be a not resistor. Here is a resistor. Here is a resistor. And ground. Let's make this a 1K. Make that a 1K. Connect them up. So here you see V1 is 1/2 of V4. V4 is twice V1. If I run this, again my input, what was it? A 2 volt sine wave. V4 should be a 4 volt sine wave. So when I simulate it, here's what I get. Again, V3 is the voltage to the base. I don't really care. Here's the output. Output is twice the input. So you can build push-pull amplifiers with a gain if you want. So this is typical problem you see on the quizzes. They had this circuit. If the input is plus 2 volts, find the voltages and currents. If it's minus 2 volts, find the voltages and currents. So let's start at plus 2. And we'll pause for a second. Let you try to solve for the voltages and currents at plus 2 volts. Okay, then picking up, assuming you took off pause now. If you're plus 2 volts, V plus equals V minus, so this is also plus 2. And this right here is 2 volts. This is a voltage divider. This is 1/3 of the output, or the gain is 1 plus the ratio, 3. So this will be 6 volts. Assuming VB is 0.7, so this will be like a 6144 transistor. I have a single transistor. This is 0.7 volt drop, so this will be 6.7. Again, it depends upon the transistor you're using. TIP has a 1.4 volt drop. It's a Darlington pair. 6144 does not have a voltage drop, or has a TIP has a 1.4 volt drop. 6144 has a 0.7 volt drop. Okay. Anyway, so there's the voltages. To find the currents, let's do that in red. I've got 6 volts across 8 ohms is 750 milliamps. 6 volts across 3K gives you 2 milliamps. So the total current is 752. For a transistor, this one turns off. That's the current's going the wrong way. This one turns on. Current right here will be the emitter current divided by beta. So that's 752 divided by beta plus 1 milliamps. This will be 300 times that. So it's going to be 300 over 301. That percentage of 752 milliamps. That's at plus 2 volts. At minus 2 volts, everything stays the same, except this becomes minus 2. Current is now going up. It's 752 milliamps going left. In that case, the PNP turns on. And I'll have current going left as 752 over 301. Current going down to the power supply as 300 over 301 times 752. And the voltage will be minus 6 volts, minus 6.7 volts. So that's the push-pull. Plus voltage is push, NPN. Minus voltage pull, PNP. That's a voltage amplifier. There's another variation of it. Oh, here's the answer. Variation. I can also build a current amplifier. Back in circuits, you use this symbol, a current source. That's what this is. To use the push-pull as a current amplifier, I need a current-controlled voltage source, also known as a resistor. That's what this one does. This converts 1 volt into 1 amp. There's also 0.1 ohm resistors. 10 volts is 1 amp. 10 ohm resistors. 1 volt is 100 milliamps. They actually do make 1 ohm resistors. This is what they're for. Kind of the way this works is, suppose X is 5 volts. Let's get the colors. Suppose X is 5 volts. Well, V plus equals V minus, so this is also 5 volts. And this is 5 volts. 5 volts at 1 ohm is 5 amps. That current comes from over here. This is 5 amps. So 5 volts means 5 amps. Minus 5 volts means minus 5 amps. That's a current source, or voltage-controlled current source. The reason you want to use current is for LEDs, brightness is current. For DC motors, current is torque. So if I want to build a car and I want the input to be the speed of the car, that'd be voltage. If I want the input to be the torque, that's a current source. Let's see, where are we at? So here's a problem. Suppose the input is plus 2 volts and minus 2 volts driving an LED. Find the voltages and currents. And we'll give you a little bit of time to solve that. You can pause the video, and then we'll pick up. So assuming you kind of went through this, let's do the plus first. If I'm at plus 2 volts, V plus equals V minus, that's 2 volts. This is 2 volts. That's my voltage-controlled current source, also known as a resistor. That gives me 100 milliamps going down. That current has to come from somewhere. This diode is turned off. This one's turned on, and will supply 100 milliamps. And for LEDs, current is brightness. That tells you how bright the LED is. That current comes from over here. So this is 100 milliamps. If you use the same transistor, where beta is 300, this will be 100 over 301 milliamps. And this will be your current gain, 300 times IB, which is that times 100 milliamps. So that's this current, and here's that current. And the voltage, if this is 2 volts, that is a 3 volt drop. This will be 5 volts. If this has a 0.7 volt drop, this will be 5.7. So that'd be a current amplifier. If you go to Circuit Lab, maybe not. And here's your answers. One kind of variation. In lab, if you have a plus-minus power supply, then use a push-pull amplifier. For some of the labs, we just have access to 5 volts. For example, if you're just using some of the kits from Amazon, they have a 5 volt power supply and ground. There isn't a minus. I can still do an amplifier just using a 5 volt power supply. And here kind of the idea is I'm limited between 0 volts, that's one power supply, and 5 volts. If I center my sine wave on 0, that's not going to work. This part is going to get clipped. So I'm going to get some distortion. Instead, what I want to do is I want to take the input and center it at 2.5 volts. So there's my sine wave. I can then amplify it. And what happens is 2.5 volts looks like circuit ground. 0 is an arbitrary number. So like think about birds on a high voltage line. They think 13,000 volts is ground. We think earth is ground. They're both perfectly valid. Just don't tie the two together. I could treat this as circuit ground, so that's 0 volts for the circuit. This behaves as minus 2.5 volts for the circuit, and plus 2.5 volts. And the reason for doing that is I want to have a sine wave going in and out, again, relative to circuit ground. But in terms of absolute, I can't go below absolute 0, because that's my power supply. I can't go above 5, that's the other end of my power supply. Go above that, I'll get clipping. Keep between 0 and 5 volts, I can get a sine wave out. That's what this does. I'll take my input, shift it by 2.5 volts. So like if this is 2.5 volts, this will be 2.5 volts. If I'm using the 3144, 6144, this will be 3.2 volts, and everything's fine. I'll have 2.5 volts at the output. If this goes plus or minus, this will go plus or minus. I still have a sine wave out. That's a variation when you have a single-sided power supply. Essentially what happens is, for the push-pull amplifier, I never go negative, so I don't need the pull part, the PNP, because it never gets turned on. If I don't use it, I might as well just not build it. So this is the push-pull amplifier with the PNP taken out, and the minus power supply taken out. So here's a circuit. One way to build an amplifier if I only have a single 5-volt power supply. What I'm going to do is I'm going to generate a 2.5 volt source. Here's the voltage follower. So this is 2.5 volts, my circuit ground. Here's my headphone for my cell phone. I'm going to treat ground as 2.5 volts. So here's my AC signal going up and down relative to ground. Find the voltages when I'm at plus 0.3 volts relative to circuit ground and minus 0.3 volts relative to circuit ground. So let's start out at plus 0.3. If this is actually 2.8 volts, which is, this is now all relative to earth ground, it's 0.3 volts above circuit ground. This is 2.8, V plus equals V minus. This is 2.8. I've got 0.3 volts across 1K. That would be 0.3 milliamps. That current has to come from up here. This is also 0.3 milliamps. 0.3 milliamps times 3K is 0.9 volts. 2.8 plus 0.9 is 3.7 volts. This is 3.7 volts. And if that's a 0.7 volt drop, this is 4.4 volts. And the current is 3.7 volts at 8 ohms is something. 463 milliamps. That current, this has a gain of 300. This current will be 463. Let me spell 463. 463 over beta plus 1. Yeah, about 1.5 milliamps. The op amp can do that. And this will be the remainder. Okay, so notice, this is relative to circuit ground, 0.3 volts. 0.3 volts above 2.5. Here's a gain of 4 amplifier. This is 1.2 volts. 4 times that relative to circuit ground. And this is still 1.2 volts above circuit ground. So let's try again when the input is 2.3 volts, 0.3 volts below circuit ground. So pause the video and try to solve that, and we'll be right back. Okay, so suppose this is 2.2 volts, which is 0.3 volts below circuit ground, so that behaves like minus 0.3 volts relative to circuit ground. In this case, this is 2.5 volts. Here's my 2.5 volt reference. Again, this is half of 5 volts. This is a non-inverting amplifier. V plus equals V minus, 2.5 volts. Here's 2.2 volts. This is V plus equals V minus. This is 2.2 volts. For current, I have 0.3 volts across 1K. Let's see, funny looking red. 0.3 milliamps. This is 0.3 milliamps. 0.3 milliamps times 3K is 0.9 volts. 0.9 volts below 2.2 gives you 1.3 volts. This is 1.3 volts. 1.3 volts at 8 ohms is 163 milliamps. And this is the 163 milliamps over beta plus 1. And here's the remainder. So again, this is minus 0.3 volts relative to circuit ground. Minus 0.3 times 0.4 gives you minus 1.2 volts relative to circuit ground. So this is 1.2 volts below 2.5, which is 1.3 volts. This still works. Actually, the voltages are always between 0 and 5 volts, because if all I have is a 0 volt, 5 volt supply, I need it. By treating 2.5 volts like circuit ground, everything works. I have an amplifier, gain of 4. Later on lectures, if I have a filter, I can filter the signal. Everything is relative to 2.5 volts. So I have my sine waves riding on a 2.5 volt reference. I can amplify it, filter it, everything relative to 2.5. When I'm done, I can drive the 8 ohm speaker. And what you'll see is the 8 ohm speaker kind of pops. It always has a 2.5 volt offset, so it's always drawing power, but it's going up and down relative to that 2.5 volt offset. And here's a solution. Same thing we just went through. One last variation. You can actually go plus or minus with a single-sided power supply. It's a little bit tricky. What you do is, here's my push. X goes between, say, 1 volt to 4 volts. That'll push this guy, and B plus equals B minus. This goes 1 to 4 volts. And this will be up by 0.7. Over here, I'll have 5 minus X, and I can do that with an instrumentation amplifier. So if here's X, here's my instrumentation amplifier, plus minus. That goes to ground. This goes over here. I want to gain a 1, so there's your 1K, 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 1K. This is not X, this is 5 volts. Here's X. The output is 5 minus X. And that'd go right here. What happens is if X is going 0 to 5 volts, this guy over here, call that Y, is going 5 to 0 volts. So this is going to be X, here's Y. The voltage across the resistor is the difference. Over here, the difference is minus 5 volts. Over here, X minus Y is plus 5 volts. And in the middle, when they're both at 2.5, the difference is 0. So I can go minus 5 volts to plus 5 volts across the load with only a 5 volt power supply. And I'm doing that. None of these are actually ground. If I ground it, the circuit doesn't work. X is going between 0 and 5. Y is going between 5 and 0. The difference between the two is minus 5 to plus 5. Make that a motor, and I can make the motor spin backwards at 5 volts. I can make the motor spin forward at 5 volts. Or I can make it stop. That's kind of one trick you can do with a single power supply. I can make a motor go forward and reverse. That uses 2 push-pull amplifiers and 2 op amps. A little more complicated. But to analyze it, for example, like if I have 4 volts in, this is 4 volts. This is 5 minus 4, 1 volt. This is 1 volt. I've got 3 volts across my load. And this transistor turns on, that one turns on. So this way is current. Let's see, This applies a little bit of current, turning this one on. This sinks a little bit of current. This is pull. If I have 1 volt in, this is 5 minus 1, 4 volts. In that case, this becomes 1 volt, 4 volts, current's going this way. This NPN turns on. So this is now sourcing current, that's push. Current's going down, so this one will also turn on a little bit. This is pull. So I can't actually get plus minus 5, actually it can be like plus minus 3 volts out with a single 5 volt supply. Not quite the range because I can't get to 5 volts directly because you lose some voltage through here. I won't quite get to ground exactly because I have some voltage drop across here. So it's more like, 1 to 4 volts relative to the load, plus minus 4 volts out with a 5 volt supply. So in summary, a push-pull amplifier allows an op-amp circuit to drive a low impedance load, such as the DC motor or a speaker. You can operate it as a voltage amplifier and use that to drive a speaker or control the speed of a motor. I could use it as a current amplifier and use that to drive an LED or apply torque to a motor. Basically an all-around useful circuit. What's nice about the push-pull amplifier is it's cheap. For $1, I can turn my oscilloscope, my wimpy op-amp, into an op-amp capable of 3 amps. And that's lecture number 3 for ECE 321 Analog Electronics.